Good afternoon. My name is Keith Hare, and I'm going to spend a few minutes talking about the property graph database language GQL and how it compares to the SQL language. So who am I? I work for a company called JCC Consulting, which specializes in high-performance database systems, data replication, migration, and database administration. Along the way, I've gotten involved in the Database Language Standards Committee, the SQL and GQL standards, and I've ended up as the convener of the International Committee and the vice chair of the US Committee for Database Languages. For several years, I've also been working with the Neo4j Langstar team, specifically on the GQL standard, on standards diplomacy, and on GQL strategy. So last year, ISO published a new international standard for a property graph database language called GQL. So what is a property graph database? What is GQL? And how does GQL compare to SQL? What I'm going to try to do in this presentation is to provide an introduction to GQL and a quick introduction to the differences and similarities between GQL and SQL. So I'm going to talk about a bunch of things. We'll go through this in more detail. So standards. There has been an SQL database language standard, technically ISO IEC 9075 Information Technology Database Languages SQL, since 1987. This describes tables and constraints and queries against tables and constraints. There have been multiple revisions published since the initial version in 1987, most recently in June of 2023. There are now 11 parts to the standard, and the new part last year was property graph queries in SQL PGQ. I'll come back to that. In April of 2024, a new database language standard was published for GQL specifically for property graphs. So SQL talks in terms of tables and constraints and columns. GQL talks in terms of nodes and vertexes or edges and relationships. So take a step back. Why standards? Why standards for database languages? Database language standards help unify the marketplace and reduce chaos. So instead of competing on the language, database vendors can compete on performance and reliability and adherence to the language standard. With a standard, tool vendors have a consistent interface, so it is easier for a tool vendor to work with multiple database products. Database users who understand one database product can easily transfer their skills and knowledge to another database product. So there is some value to standards. Standards seem a bit complex, but there's definitely value to having a standard. What is a property graph? Well, property graphs talk in terms of nodes and relationships, also sometimes called vertices and edges. And these have an identity so that they can be distinguished. A node and an edge can have 0 to n labels and 0 to n properties. The edges can be either directed or undirected. So a directed edge implies a hierarchical relationship. An undirected edge implies a relationship that where the different nodes are equal. The important thing about a property graph database is that the relationships between the data are actually stored as data and can be queried. I've used the term nodes. Sometimes you'll hear me and other people say vertexes. They're synonyms. Nodes can have labels and properties. Edges, sometimes called relationships, can have labels and properties. With an edge, you have a start node and an end node, although if it's an undirected edge, it basically just has two nodes. They aren't really a start node and an end node. Relationships are tracked in the data. There have been a number of use cases identified for property graph databases, including fraud detection and analytics. A property graph database is actually ideal for describing a computer network or utility transmissions or a water system. That can be used for real-time recommendations. More recently, property graphs have been used a lot with AI and machine learning and retrieval augmented generation. So there are lots of use cases for property graphs. Quick side note on the terminology. Different vendors use different terminology. For example, Oracle uses vertex and edge. Neo4j uses node and relationship. When we wrote the standard, we compromised and allow for both synonyms, but generally we use node and edge in part because those are the shortest words. So a side-by-side comparison, and we'll come back to some of the details later. The most important thing on this slide is that in SQL, you have to know what the relationships are between data when you write the query. So you have to specify the relationship in the query. In GQL, relationships are stored, or they can be stored as data. And if they're stored as data, then you can query the relationship to find out that the relationship exists. There's a couple other differences like case sensitive versus case insensitive, nested composition versus linear composition. But the biggest difference is having to know relationships when you write the query in SQL and storing the relationships in the data in GQL. Both languages are non-procedural. That is, you tell the database what to do, not how to do it. Okay, an SQL. In a simple SQL database for personnel data model, I might describe the data model looking something like this, where we have employees that are related to job history because of an employee ID. An employee can supervise a particular job. An employee manages departments. Job history rows have job codes, and so on. This is a simplified view of a database because this fits on a slide and in the examples. So we're going to have some tables: an employees table, a job history table, a jobs table, a departments table, and they're going to have primary keys. The employees table is going to have a primary key that's the employee ID. Job history is going to have a primary key of employee ID and a job start date that uniquely identifies the job history row, and so on. So we have tables, we have columns, we have constraints, and things like primary keys. So create table in SQL is going to look like this: create table employees, where we have a column name, a data type. We might have primary key constraints, et cetera, et cetera, et cetera. We can operate on data. We insert data with an insert statement. We select data with a select statement, select some columns from employees where employee ID is equal to 00160. We can update the data and we can delete the data. This is sometimes described using the acronym CRUD: create, read, update, and delete. But I sort of prefer insert, select, update, and delete. So this example adds a job history row, and you could think of a job history record as somehow mapping a relationship between an employee and a department with some information about the job start and maybe some information about the type of job. In the sample database that I borrowed these examples from, job history has constraints defined. So there's a requirement in the database that employee ID must exist in employees.employee ID, job history.job code must exist in jobs.job code, and so on. The constraints are evaluated when by the database when the data is inserted, modified, or deleted. So the relationships are enforced by the database, but they don't actually show up automatically in queries. So for example, if I want to find the employees in the engineering department, I have to select things from from job history and employees, and I have to include in my query the fact that employee ID from employees needs to be equal to employee ID from job history. So the person writing the query has to know the relationship between employees and job history. More complicated query, what connections does Oliver have? So to write this query, I have to know that an employee has a connection to a job history record, and that an employee has a connection to departments, because the employee ID in department and employees is equal to the manager ID in departments. So the query writer has to know the relationships between Tolliver and anything else. And then you can write a query that says, give me the stuff with this relationship, union all the stuff from this other relationship. A little more complicated query, who works in the department Tolliver manages? So again, I have to go look at multiple tables, employees, departments, job history, and employees. So I have to know that an employee has a job history record. I have to go to departments to find the departments that Tolliver manages, and then I have to use the job history records to find other employees. So I'm going to have a 4-table join with a more complex where clause. In this case, Tolliver shows up on both sides of this relationship because Tolliver actually works in the department that he manages. SQL has transactions. The idea is that you begin a transaction and you have some level of queries and data modifications until a transaction is committed. No other transaction can see the result of the modifications. When I get to the end of a transaction, a unit of work, I can say commit or rollback. If I say commit, the modifications are saved to the database and they're visible to other users. If I say rollback, the modifications are undone and none of the modifications are visible to any other transaction, any other concurrent user. So pretty much classic transactions in SQL. All right, so what about GQL? Well, wait a minute. This logical design looks pretty much like the logical design for the SQL version. And that's because it is. We're thinking the same way about the data. There's just a few somewhat different things that we do with the data in a property graph database in GQL. So as I mentioned, we have nodes that can have labels, which are tags. You could compare a label or a set of labels to a table name, but they're a little bit different. We have properties, which are pairs of property names and property values. You could think of properties as similar to columns in an SQL table, but they're close, but they're a little bit different. The edges can also have labels and properties. In addition, they have a start node and end node. for directed edges and 2 endpoints for undirected edges. So how do I insert data? Well, I insert. In this example, there's a label that is identified by the colon, and the label is employees. And then I list a set of pairs of property name, property value, property name, property value. One difference with GQL over SQL is that the label names and the property names are case sensitive. So I have multiple properties. To add a job history row, a job history node for an employee, I would do another insert where I say insert, and I'm going to have a label of job history, and I'm going to have an employee ID, start, job start, department code, etc. Any names not mentioned here are implicitly null. So now, how do I query? Do a match. I want to match the nodes with an employee ID of 00160 and return A, where A in this case is a correlation name that's defined as part of the match statement and can be referenced to other places in the query. And so this returns 2 nodes, one with a label of employees and one for a label of properties, of job history with different properties. So I have 2 nodes. I now want to make sure there is an edge between an employee node and a job history node. And so what this example at the top of the slide does is a match query where it's basically matching nodes, 2 different nodes, one an employee's node and the other a job history node, and it's adding the criteria where e.employee ID is equal to jh.employee ID. So you look at this and say that's real similar to SQL because it is. However, the next part is I'm going to add another statement, another substatement in this more complex statement, and I'm going to insert an edge called hasJob, where the start node is the employee record I just retrieved, E, and the end node is the job history record I just retrieved, referenced as JH. And just to see what's going on, I'm going to return the start node and the end node and the relationship back to my query. So the syntax here is that nodes are designated with parentheses, edges are designated with arrows and brackets between the 2 nodes. So in this case, I said that H, which is a correlation name because it's to the left of the colon, hasJob is the a label of the edge name, and it's between 2 nodes that are in parentheses. I could insert multiple edges. In this case, I'm going to look at all of the nodes for employees and job history, all the nodes for job history where the employee ID is the same, and I'm going to insert edges, relationships between those nodes. I'm going to do the same thing for job history to departments and another that relates job history to jobs. So I'm inserting the relationships in the data so I can query it later. I can also add properties. In this case, I'm going to add a property that says that the nodes where the last name is equal to hair are nearsighted. and I can retrieve that. I can also remove a property by using the remove. So set adds a property to whatever the current node is or edge. Remove removes a property. And yes, I am nearsighted. I also need to delete. The thing about delete is that if I have an edge between two nodes, you don't want to delete the nodes and leave an edge there. And so there's two statements, detach and delete. So in this example, I'm doing a match. I'm finding properties, sorry. I'm finding nodes where first name is equal to Keith and any relationship to any other node, and then I'm going to do a detach delete for those. If I had left off the detach in this example, the delete would have failed because there were attached edges. So far, everything we've done has been schemaless. So labels and properties were defined by inserting data. You might ask, won't this lead to chaos and confusion? Well, yes, it could. And so if you're using schemaless, you have to pay attention to the data that you're inserting and probably have some work occasionally to clean up completely bogus data. What if you actually want to control the schema? We'll come back to that in a few slides. I want to get a couple of other topics in first. What about constraints? I haven't said anything about constraints so far. In the initial version of the GQL standard, we didn't get constraints done. We talked about it, but there came a point where we had to get a standard done, and things that were incomplete got deferred. So this is a possible addition for a future version. The syntax might look something like create constraint for nodes with a label employees and require that a particular property be unique. Or create a constraint for job history and require that the combination of employee ID and job history be unique. This is in the standard, this is future work. Let's do some other queries. So if you flip back to the slide where I was talking about employees in the engineering department in SQL, this query is a little simpler because I don't have to know what the relationship is. I just have to, I'm able to query the relationship. So this allows me to go to job history, employees connected with job history, where the department code is equal to ENG and job end is null. And then I'm going to return the department code, the last name, and the first name. So the edge, the relationship between employees and job history is data that can be queried as opposed to something that I have to know the details of as I do in SQL. So what connections does Tolliver have? Give me employees where the name is Tolliver and a relationship. In this case, I'm using the correlation name W to whatever. And we find that Tolliver has a job with a job history node and manages a department with a department name. In this example, I'm actually also returning the relationship because I can treat the relationship as data. And this is where a lot of the power of the property graph model comes in. I can store the data, the relationships between the data, the relationships between the nodes, and query that later without having to know what it is. Who else works in the department? Again, the match statement here gives me the same data as the example I used in the previous in SQL, but this query is simpler. So any data that deals with relationships, as long as the relationship has been stored in the data, the query is going to be simpler in GQL than it is in SQL. Property graphs fit well in visual representations. And there are a number of tools for visualizing the property graph data. So in this case, Tolliver manages board manufacturing department, has a job where he works in the board manufacturing department, and several other people also have jobs in the board manufacturing department. Visualizing property graph data is a whole topic unto itself, and this is just a simple example. There's all sorts of things you can do when you get queries that return larger chunks of data. The core of querying is called graph pattern matching. So it's a really powerful set of capabilities for expressing patterns. There's also what are called quantified path patterns and cheapest path queries. And I'm going to give you a couple of introductory slides into these capabilities, but not go into them in detail because it just doesn't fit in this particular talk. So graph pattern matching, I can have a simple query where I can have label expressions. So this says, give me the nodes where the label is person and either an employee label or an intern label. Could also be both. I can do a path pattern union that basically takes two queries and gives the result as a union. I can do multi-set alternation. I can do quantified path patterns. The first example is looking for a label called boss, where boss has a relationship knows with some other node, and there are either one hop or 5 hops. I can do filtering, I can do unions, I can do alternation, I can do aggregation, and any combination of this. This slide in and of itself can probably fill, going into the details and some examples, could probably fill about another hour relatively easily. So I'm not going to go into the details today. Okay, I've got a database, I've got updates, I want to have transactions, I want to do a begin transaction, do some work and either commit or rollback. Wait a minute, this looks identical to SQL transactions. It is identical to SQL transactions because the requirements are the same, it's just the way the data is represented is different. Now, in previous examples, I was looking at a schemaless or an open graph. There was no restrictions on the content. I could insert any node, build any edge between the nodes. So it's relatively easy to get started, flexible. It can lead to chaos if you're not controlled, but it is possible to sit down and start loading data and figure out the issues later. This is particularly useful when you don't have a good understanding of the data and you need to be able to write queries to understand the data better. However, some applications require restrictions, what's often called a schema. In GQL, this is called a closed graph type. And what you do is you create node types. You create a graph type with node types and edge types. And then you can create a graph from that graph type. And the graph is constrained by the graph type. So a simple social network graph type example. I've got persons, I've got cities, I've got pests. I have a couple of relationships, one that a person lives in a city and another that a person knows another person. Create a graph that is of the social network graph type. And I can then insert things like a person with a name of Keith and a last name of Hare. Notice that I'm actually inserting a whole relationship here. I could insert a pet, in this case, a dog by the name of Winifred. However, this last statement, matching Keith and Winifred, I cannot insert this has-pet relationship because the has-pet relationship is not defined in the graph type. So the graph type controls or constrains the data that can be inserted into the graph. By the way, I do have a dog by the name of Winifred. So the property graph stuff looks interesting, but what if you already have a large amount of data in an SQL database and a lot of application codes? You have a couple of options. One is that you could extract, transform, and load data into a property graph database, but then you have to keep the data replication up to date. And so that's not completely always something that's going to be able to do, which is why the Standards Committee, SC32WG3, also added a new part to the SQL standard, something called SQL PGQ. And this part was published in June of 2023. So this adds sort of two major capabilities to the SQL standard. One is the ability to define a property graph view on top of existing SQL tables. And the second is to query a property graph view in an SQL from clause. So this brings the power of property graph queries to existing SQL data. If you looked at this as a Venn diagram, there's this SQL language, this new part, SQL PGQ, there's the GQL language, and the common component between them is the graph pattern matching language. Cover the two standards. I spent a lot of time on these, and so I'm actually pretty proud of the work we got done on these standards. So what does this look like? I would create a property graph. In this case, I'm going to call it personnel. And I have a number of vertex tables, node tables. There's one, I'm going to use the employees table with a key of employee ID and some number of properties. I'm going to use the jobs table with a key of job code and some number of properties. I'm going to have edge tables where I have job history as an edge table. I've got an employee ID, and that references employees' employee ID. The destination key of, so that's the source key. The destination key is job code that references job code and jobs, and it has some properties, job code, job start, et cetera, et cetera, et cetera. So this is how I would define a view, a property graph view on top of an existing table with employees, job history, departments, and so on. Then in the from clause, in the select statement, instead of listing a table or several table names, I would include a graph table, which is a function, looks like a function, where the first parameter is the graph name, in this case personnel, and then I have a match query. Match employees, JH to get the job history relationship, and jobs. And then I tell the match or the graph table function what columns I'm going to return from this query. So the first query is getting employees and their jobs. The second query adds the qualification job end is null. In this database, if job end is null, that means it's a current job. And so that just gets the current jobs. So this looks a lot like a property graph query in GQL, except that it's in a graph table function in SQL. So a little more comparison. The important point here is that we can have graph pattern matching queries in both SQL PGQ and in GQL. GQL is a full database language that does create, read, update, and delete. Also create graph type, et cetera, et cetera, et cetera. The graph pattern matching queries in PGQ in the graph table function support reads. So it's read-only. GQL is read-write. To update the underlying data in an SQL PGQ environment, you have to use SQL update queries. Graph pattern matching. So in SQL PGQ, I would say match A is person with an edge. E is friends. Note that I'm using an is instead of a colon here, but it's colon and is are synonyms for label expressions. But the part in blue is exactly the same for SQL PGQ as it is for GQL. All right. So what products do all of this? Well, for SQL has been around for a long time, so there are lots of products: Oracle, Microsoft, MySQL, MariaDB, Postgres, et cetera, et cetera, et cetera. For SQL PGQ, the number of implementations is still a little bit small. Oracle version 23 AI implements significant portions of the PGQ specification. Not quite everything yet, but significant portions. There's a database out of the Netherlands called DuckDB, and there is an add-on DuckPGQ for DuckDB. PostgreSQL, there's a prototype PGQ implementation. I haven't actually played with that yet. GQL, there are a number of property graph vendors. These are all relatively small, but they have the potential of implementing GQL. Two of them have now actually published GQL conformance statements on Neo4j and a company out of China called Altipa. So there are beginning to be GQL implementations that actually have documented their conformance to the GQL standard. So in the SQL standard, we've had 9 editions since 1987. So we've incorporated new features over time. Provides consistency across database. It's not 100% consistency, but it's not bad. It's better for you developers that are moving between implementations than it is for moving code. But it's not bad. We published a new edition in June of 2023 that includes SQL PGQ. The GQL standard was published in 2024, April 12th, but who's counting? It's a full property graph database language. One of the important points is that we were able to keep the graph pattern matching portion of the language identical between SQL PGQ and graph pattern matching. For both of these standards, we're now working on the next edition. One of the important capabilities actually in the next edition of both SQL and GQL is going to be support for vector data types that support some of the AI retrieval augmented generation capabilities, but that's beyond the scope of this talk. So let me know if you have questions, and I will do my best to answer them. Thank you.